panel event. So now we're switching gears and we're going to talk about the physics of underwater sound. And I remember at the ICFT last year having some conversations with Michelle Heupel especially, and she was very passionate about the fact that, you know, this technology that everybody here uses, it operates with sound underwater, and so we really need to understand what factors can be influencing it. And I thought, oh my gosh, you're right, I need to know how sound acts underwater. I haven't taken physics since high school. I should probably learn about this. So talking to John Pye, he said, I know the perfect guy who could give a lecture on this, and he talked about David Barclay. David Barclay is a CRC chair. He studies sound and sound propagation in lots of different water environments, but especially in deep water, right? Yeah, and he's actually writing a paper on this specifically. So he's currently writing a paper about how sound can affect acoustic telemetry. And so he's going to talk for the next 30 minutes about the physics of underwater sound. So thank you so much, David. You can put this here. You can put that on, I think, too, Lisa.
Okay, great. Well, luckily most of the physics of underwater sound is high school level. I'm serious. We're going to talk about some really simple stuff here, and but can have a really profound impact on how the performance of your receivers, your fish tag receivers. So the outline, just a quick, shortish talk, very basic question: what is sound? And we'll talk about this. Yeah, these concepts that are familiar to all wave propagation. Optics, electromagnetic, surface waves in the ocean, right? And then I'm just going to talk quickly about the SONAR equation, and then a little bit of a study, just a modeling study, coming from the complete other end. No experience in the field. What can we do from physics up to predicting the detection range and performance of receivers, and specifically the Halifax Line receivers. Okay, so first question you got to start with: what is sound? And you know, basically it's molecules crashing into each other. Denser, refracting, less dense, and that communicates some signal. That signal propagates with some speed, right? So the speed of sound. And the amazing thing is that in a dense material like water, that's a nearly lossless signal. So a nearly lossless process, right? So it can travel very far distance. And the speed of which the signal goes depends on the properties of the material itself. Okay, so like I said, there's similarities between all these wave propagation phenomena. So I have a question for you all. Why is the ocean blue? Why does it look blue? Not sound, electromagnetic, optics. Why does it look blue? Oh, in the back there. Absorbs every color but blue. Yeah, exactly. So this is the absorption coefficient. This is a log scale here. So the lower on this scale, the less the energy is absorbed, the optical energy, and the higher, the more it is. And you can see this little rainbow here that's the optical spectrum, the part of the frequency spectrum that we can actually see with our eyes. And blue is the least absorbed. So that's why the ocean looks blue, okay? So we can ask the same question with sound. And this is the same figure here with sound. Here you have frequency going from very, very low frequency up to high frequency. I put some things to orient yourselves here. Your baleen whales, so the low calls. You got the piano keyboard. That's like the highest note in the piano keyboard, the lowest note. A sub. Submarine. I don't have any GIFs. There's no GIFs in this one. Nathan has some nice gifts. That's as good as I get. You got your ADCP here, and here's your Vemco fish tags, 69 kilohertz, 180 kilohertz. And so you can just look on this figure and say, okay, obviously we should be using fish tags that are at like 1 hertz, but that would, the size of the speaker. Think of your subwoofer. 1 hertz is big, right? You need a huge speaker. So if you want something small, it's got to be high frequency. The the absorption, so this is just the energy absorbed by the water itself, is about 20 dB per kilometer. So the decibel, the dB, is just a relative measure, and 6 dB means half the power. So 20 dB, you're half, and a little bit. So you're a little more than an eighth of the power over 1 kilometer. So that's why these detection ranges are so short. Now that's if you just had water and nothing else around, and it was all just one isotropic, perfect bath. So that's the first thing to know. And I should say that depends on temperature, salinity, pH, a bunch of things. Speed of sound, the other thing. So I said, the speed at which that signal propagates has to do with the properties of the media. So in air, it's about 330 meters a second. It depends heavily on temperature. And in water, it's about 5 times that. And in very dense things, it's very, very fast, right? So yeah, there's some kind of intuitive physics in there that you should consider. And really, there's some great examples that we experience all the time that that involve these changes in density, these changes in temperature that can manipulate the way a sound propagates in the media. So here's the classic one. You want to go camping for the weekend. You find a nice quiet lake, and you're over here camping, and there's some usually known as yahoos blasting the stereo across the lake, and you're like, why can I hear all the way across this lake so well? And, well, it's this idea of refraction, right? So you have the cold lake. It's making this cold, slow layer of air here. And there's a warm layer where the sound travels faster up there. And so what happens is the sound rays come up and they curve back towards you. And you can hear like super far away. It can be really, really incredible, right? Sometimes you even get rays that are sort of bouncing along. That's why you can hear that conversation all the way across the lake. So keep in mind, refraction. Again, high school physics, right? But good thing to keep in mind when you're looking at the ocean, okay? So here's the canonical deep ocean. Here you have your Monk sound speed profile. So you have warm, salty water at the top. As you go down, the temperature slows the sound speed down. Then as you go down even further, the pressure speeds the sound speed back up again. So you get this kind of sound speed profile that looks a little bit like a lens, okay? And for your sound source generated at the surface, you can have rays that get trapped around this minimum, this kind of sound channel axis, it's called, right? So you can get basically sound rays that are propagating very, very far distances. You can get rays that are trapped in a surface duct that are bouncing off the surface of the ocean, and all because of this refraction. And this is a super powerful thing, right? So you can have at low frequency sounds where that absorption is super, super low, right? You can have a ship or a whale or submarine generating sound, gets into that sound channel axis, and it can travel hundreds, thousands of kilometers. And so here's just the historical interlude. This is the world's formerly greatest living oceanographer. He just died last year, Walter Monk. He did this amazing experiment where they went out to Heard Island here. They let off a couple of tons of dynamite or something like that. And they could hear it all the way in Bermuda and up actually around on the west coast as well. And so it was all just this idea of putting sound into that deep sound channel axis, and it could essentially go on forever. Now, obviously when you start putting boundaries in there, they become important. So we have refraction, we had absorption, we also have to think about reflection, right? So here's a shallow water environment. You have a source at the surface there, it's bouncing off the bottom, it's bouncing off the surface, and you want to understand, well, how will that impact the transmission loss, or how much energy is lost every time it goes out in some range. And so the question is, what governs the physics of the reflection of a sound wave at an interface? And the simplest answer is just acoustic impedance. So the impedance, you may also remember from high school electronics. No? Anybody? No? Okay, density and sound speed. So there's an analogy to how current flows through a resistor. But the idea that it's the product of the density and the sound speed of a material. So for instance, at the surface, right, you have very, very low density, right? The density of air is very low compared to the density of water. And so essentially, the impedance is like 0. So you get a perfect reflector at the surface. So if you had a perfectly flat surface of the ocean and you looked at it with sound, it would look like a mirror. Your rays would bounce off without losing any energy. In the seabed, on the other hand, you can have a very hard bottom, which is very high density, high sound speed. It can be reflective. A soft bottom, which would be kind of an equivalent density to seawater, right? A mud can be sort of almost the same 1,000 kilograms per meter cubed. And so if it can be more absorptive. It can basically be acoustically transparent. The energy can propagate into the bottom and you won't get much of a reflection. And so all these things depend on what might be at your study site, the sediment properties, grain size, porosity, density. Now the other thing, of course, is that I've drawn these as perfectly flat surfaces. You can get a windy day and start to get some really rough surfaces up there, you know, at the surface, and that can really impact how things reflect off the surface. You can really, you can imagine this ray, instead of bouncing off a perfectly flat surface, there's a little wave there, and it scatters it, and so it can be quite complicated considering all of these things. So those are all the very basic wave propagation things to consider. Now, I just want to put this in here. This is just to show you that even with this basic knowledge, you can do some pretty interesting research. So this is a study we did recently, and what we did is we put 2 hydrophones here in a muddy sediment. We had an elastic basement, an elastic muddy sediment, and we listened to the noise. So the sound of breaking waves was reflecting off the sediment. We came up with a statistical model, and the basic idea was that just by listening, we could compare the noise in this waveguide and figure out what all of these parameters, so the compressional wave speed, the shear speed, the attenuation, so we could just listen and understand what the ocean was made out of, basically, what the seabed was made out of. Similar to, you can imagine you're in a room and you can figure out if it's concrete walls, glass walls, or has carpet or whatever just by listening, right? So do the similar type of stuff in the ocean using this super basic physics. So one last thing we need to consider is geometric spreading loss. Again, something you might remember from high school. And the basic idea is that if you have a source that's emanating some sort of energy, let's say it could be optical, it could be acoustical, as the waves propagate outwards, they have to cover more and more surface area, right? 4 pi r squared in the case of just a boundless, limitless, infinite media that you're working in. And so energy loss goes as r squared. And so decibels are a measure of relative energy, so this is why they're such a convenient unit to use. And so basically if the energy loss goes as r squared, the loss in decibels goes as r squared, the log, you take it out, 20 log r, right? Remember that? Okay. And for a cylinder, so here I have this sort of shallow water. So now you imagine that your environment's like it's trapped between 2 boundaries, and imagine you have perfect reflectors on either boundary. Now your energy is just propagating out like a cylinder. And so the area now is 2h pi r. Energy loss goes down as r, so now there's no exponent to take out. You just have 10 log r dB, right? So these are super simple models to right away get a handle. Okay, if I had a tag in an ocean with no boundaries and no absorption, this would be a really nice model to work with, okay? That's it. That's all you got to know to understand transmission loss. So it's very basic, okay? Now I have another historical interlude. I want to talk about putting sound in the ocean. So you're actually putting sound in the ocean. And this interesting fact, the first person to ever make an underwater speaker was a Canadian, Reginald Fessenden. And it was actually used, they would put these big low-frequency sound sources. So again, this is like probably around 10 to 100 hertz. So you can imagine that, a little impractical to tag a fish with that. And mariners would actually go in the hulls of the ships on foggy days and listen for the sound sources to guide the ships in when they couldn't see anything. So this was like an interesting idea at the time, but I have a question for you. What great world event happened that brought much fame and fortune to Reginald Fessenden and this technology? Happened the year after. Anybody? Anybody? Not war. Titanic. Yeah, because he figured out that not only could you hear, you could listen for the sound, but you could actually make the sound. It could send it out. It would reflect off of something like, say, the seabed or an iceberg, and it would come back. And if you hear that reflection, you go, there's an iceberg there. Be careful. And he suggested we put it on these ships, and yeah, it really helped push the thing forward. Now, of course, then the war as well. They figured out, it also reflects off submarines, and that was a whole other thing. And that's where he came up with these simple equations known as the SONAR equation. So there's a whole family of these types of equations. And again, because you're using decibels, it's all a relative measure, and they're log, right? So log A times B is log A plus log B. Right. So you can do simple things like this. Okay, the signal to noise ratio, so the amount of signal above the noise level that I'm receiving, is equal to the source level minus the transmission loss. That's all the stuff we just talked about, minus the noise level. So there's some background noise level, let's say, in the ocean. And so this is your super simple model, and with no fish tag experience, the complete opposite of Nathan, this is where you're going to start to think, well, what is going to be the detection range and the detection range and maybe the detection efficiency of my receiving system. And so I put a little asterisk here. The one thing we actually need to know, this signal to noise level, that's if you just had, say, a microphone and you recorded it, you would say, here's the noise, the signal bumps up. That ratio between the two things, that doesn't necessarily mean that your algorithm that's on board your receiver that makes a detection is going to work. It might need, it might need me to speak really loud. It might need a double the signal to noise level than, say, you might need when you're visually looking at the data. So there's a certain bit of information that's missing here, but this is as close to a model that we can get to do these predictions. So if we dissect these terms a little more completely, so the source level, well, that might depend on the battery tag. I don't really know. I'm not the manufacturer. And the coupling with seawater. That's actually exactly what Nate talked about. The tag, if it's right next to the swim bladder, you're going to have reflections off the swim bladder, or it might not be very well coupled to the body, or who knows what, right? There could be the fish has weird lumps. But it's going to differ. It's going to differ. There's some physics there that's really important. For the transmission loss, well, we talked about source. So the source receiver position, so that in range and depth, that's going to be very important. The bathymetry, the shape of the bathymetry, right? The sediment type, so how reflective that bathymetry is. The sound speed depth profile, so whether it's refracting upward, downward, what's happening there. And all of these things really matter. And the position of your source and receiver next to those boundaries can be very important. If you're far away from the boundaries, they don't matter. If you're close to the boundaries, they do matter. Most of the time, these receivers are bottom mounted, so the boundaries do matter. For the noise level, a little bit trickier. So we're up in pretty high frequency, and kind of conventional wisdom would say that mostly just have wind wave noise. So we heard about that last talk, and maybe some rain-generated noise. Rain, makes little entrains little air bubbles every time you have a droplet fall. It's very, very noisy. It's like when you're in a, under a tin roof and you hear the rain banging way up there. In the ocean, it's the same thing. You might have thermal and electronic noise, so noise on your actual sensor, noise on your electronics that you might not be able to well characterize. And I put here analog to digital saturation for flow noise or ship noise. So ship noise is very low frequency, and flow noise is also very low frequency. But sometimes it's so energetic that it saturates your recording system, and you're not able to record high frequency noise. So, like in riverine systems, I could see this being a huge problem. And so then the last thing here is SONAR. We have this question: how much is needed for positive detection? Is it 0 dB, 3 dB, 6 dB, 20 dB? It's kind of hard to tell. So with all that, with that simple modeling framework, I'm just going to give a little study that I've been working on for the last little while, trying to understand if we can predict the performance of these receiving systems. And so the study site that I'm using here is the Halifax Line. It's a whole bunch of stations. There's a whole whack load of data, and the environment is varied. You're going from like super littoral off to the shelf break. So I'd imagine there's some different oceanography that's going to come into play. There's some different bathymetry that's going to be important. I just used uniform bottom properties here to kind of take that out of the equation, but also just don't really have the most data on what that is. But I used a whole bunch of sound speed profiles. So these are depth, sound speed here in the x-axis, and these black lines are tracks from gliders. I just collected them all in. Around one station, I drew a circle. These are all the ones that were collected around that circle. And then I simplified them to some representative sound speed profiles. And then used what's known as a ray tracing program. So you can calculate transmission loss using a computer program at high frequency. And this is one called bellhop. And each one of these represents range on the x-axis and depth on the y-axis. The white line is the bathymetry, and the color intensity is the transmission loss. So the darker the color, the higher. Actually, the color intensity is the intensity of sound. So, this is where your source is. It's quite bright, sends some sound out, and then as it gets further and further away, it gets less and less intense. And you can see that the sound speed profile, these are 3 different sound speed profiles, really impacts the shape of how the rays propagate. And then I did that at each station, looking in different directions, and you can see that as you go around in direction, this is some detection probability statistic. It changes because the bathymetry is slightly changing and stuff like that. These are small changes, and I was kind of curious to see, well, how much would they impact our ability to estimate the detection range. For the noise, it's a little trickier. These are some classic curves, the Wentz curves. So I was really just estimating or assuming here at 69 kilohertz that we just had wind-driven wave-breaking noise. Not always the case. There's biological noise. There's other sources of noise that might come into play here. But making the simple assumption. Now, that noise, you can read the number off of here, right? You can choose a wind speed, read a number off of here, and put that as your noise level term. But actually, there's some spatial differences to how that noise is distributed in the water column, right? And so what we did is we did a similar modeling thing where we put noise sources all on the surface, and we assumed that there was breaking waves. We summed over all of those, and that would give us the noise source at, like, say, 100 meters, 150 meters depth or whatever. So we came up with a little simple physical model, and that turned out to be pretty important when you sort the stations by depth. So this is the stations in geographical order, and then the noise level in dB, if you assume the wind is 25 knots, okay? And so this empirically, the source level is empirically determined from previous data, but its relative magnitude, according to the station position, was computed using transmission loss model, our little noise model. And so when you sort them by geographical order, you don't really see any that meaningful there. But here I've sorted them by station depth, and you can see that as the station gets deeper, the noise level increases. This is a similar type plot now. Here, what I have is the detection range for a 95% detection efficiency as a function of sound speed profile. So each one of these is a different one of those sound speed profiles that I extracted near the station and just ran the computation in the over all the different directions, and then computed the mean, and then did these whisker box and whisker plots, or whatever these are called. They're very popular in biology. We don't use them in physics very often, I have to say. And so you can see there's a huge amount of variability here, right? So you choose this speed profile. Your detection range with under our model assumptions could be 500 meters, and or it could be 750 meters. So in terms of volume, right? Think about detection volume. That's really what you need to know, right? If you're trying to understand your sample space, that's a huge amount, right? So we took the station means, and then here I have them plotted at geographical order here across the shelf break. Again, no real trend, but a very significant, basically a factor of 2 at some stations in terms of their detection range. But when you sort these stations by depth, you get a more useful statistic. So here's detection range as a function of station depth for 95% detection, 50% detection efficiency. Which is just to say this is predicting 95% of the time you're going to hear the tag, and this is predicting 50% of the time you're going to hear the tag. And you can see that depth effect from the noise is very significant. For comparison, I plotted those against, this was on the VEMCO website. This was their detection range as a function of wind speed they shared. And I plotted, here's the 95% detection line here in blue, but there's a big caveat, right? So the detection radius depends on the station depth. So here I just chose 100 meter station depth, the wind speed, so this is for all wind speeds, and the required signal to noise ratio that the algorithm needs to, the hardware needs so many dBs above the background noise to make a positive detection. That's totally unknown. So essentially, the caveat is that these lines can move up and down as much as you want with that unknown information. But at the same time, whether, so this is the same data kind of presented in a different way. Here I have chosen 100 meter station depth. I've chosen 25 knots of wind. So that gives you a certain detection range. And like I said, you can kind of move this line up and down. I have a 0 dB signal to noise ratio required for a positive detection. If that number is 20 dB, these lines are obviously going to move down, but not this variability. And so here's this is a true box and whisker plot, I know for sure here. And you can see that 30% increase in detection volume is pretty significant if you're trying to understand like population density estimate, that type of problem. So from the last speaker, of course, absolute values required experimental verification calibration. This is just a computer model for now, but it would be really amazing to try and go out and compare some of these results to some of these sentinel studies that are actually carried out, and to see how much variability can truly be there. Like I believe Nathan had that Kessel paper up where there's a plot where one day the detector efficiency is like 80% on a sentinel tag, and the next day it's 20%. And that could be just a thermal warming or some oceanographic thing happening. And if you could predict those and account for them, then it makes your data just that much more powerful. So yeah, some conclusions. We started off basically with, I want to say, yeah, high school physics was enough to get us to a pretty accurate transmission loss model. And we need those type of models to predict the time-dependent detection performance. Some of the conclusions so far, that the receiver depth, the background noise level, and detection algorithm, those determine the detection range, and the oceanographic variability influences detection efficiency of tagged marine animals. So that's working towards being able to predict that, so that could be something in studies that could be accounted for. And that's it, if you have any questions. Mm-hmm.
They're TXs, so they're transmitters.
Yeah.
Just looking at the plot right here, the noise values that the receivers measure aren't really that correlated with the reference tag detections. And I was curious about what your thoughts are on that, what the other causes could possibly be.
So the noise, oh, sorry.
Can you repeat the question?
Okay, so the question is, so you have a receiving system where you actually have an in situ measurement of background noise.
Yeah, exactly.
Right? But the detection efficiency shows no correlation with.
It's like 0.1.
Right. So, I mean, I suppose it could be the actual animals moving that are driving your detection efficiency, right? I mean, that could be one solution.
These are stationary reference tags.
Oh, they're stationary reference tags. Okay.
I was wondering, does noise drive everything, or I guess maybe physical disruptions too?
Yeah, I mean, so it's I'm kind of a little bit curious in terms of how the noise was measured. This is reported by the instrument itself. Okay.
Yeah, managed it. So.
Okay, because one thing I have been considering is the stationarity of the noise, right? So if you have, say, snapping shrimp, like you'd have, I'd imagine, down there, say you take a 10-second window of data and you calculate the noise level from that, that might be one way to estimate the noise, but is the noise stationary over 10 seconds, right? If you have lots of snapping shrimp, there'll be moments where the noise is very, very, very loud, on the order of, say, tens to hundreds of milliseconds, I guess. And so that could cause an interference, I guess, in the detection algorithm. That would maybe be my first guess at why the noise level itself might not match up with, but I don't know how it's calculated. I'm not sure if that's my hypothesis on the hot seat. What do you think? Is that possible? It's a hard thing to do. It's a hard thing to do because you are like the tag signal itself is quite short, and so you're kind of in the realm where the statistics of stationarity break down. So if you have something where you have if you imagine your noise as a distribution, you have something that has a very, very heavy tail from snapping shrimp, then kind of common assumptions are going to just not work, right? So using that mean noise level is just not going to give you an accurate, correlation. Just an idea. Not sure if I'm right.
Trying to be put you on the spot.
No, it's fine. No, it's a super interesting topic. Yeah. Any other questions?
Why do you see such a diversity of the sound speed profiles? Is it just seasonality as temperatures are changing?
Yeah, I mean, you have like short timescale processes, like on a calm day, sun shining down, you develop these like surface layers. But then you have things like eddies spinning up from the Gulf Stream that spin up onto the shelf and bring in warm water with them or cold water. So it's a huge amount of physical processes that are happening out there. Yeah, and as well as seasonality. I used profiles from the entire year as well. So yeah.
I'm curious, how well do you actually think your model would match up with testable?
I mean,
syntactic?
just depends who's asking. It's always the question. Like, so most of the work I do is like at 100 to 1,000 hertz, like low frequency stuff, and pretty much, if you went to the Navy and said, what's your detection range on a submarine? They'll give you a number, but most sonar operators would say that number is plus or minus 10 dB. Basically, there's not a huge amount of confidence in these models in general, but we're working very hard to reduce that. And working at higher frequency is somewhat less daunting because, like, you wouldn't really imagine that the boundaries play much of a factor at these super high frequencies because you're not going far enough to scatter off the boundaries many times. But, right, if we can get that one scatter off the bottom, that one scatter off the surface nailed down pretty well, then I think we could have a pretty good chance of these models being able to predict performance pretty well. Yeah. Why is the sky blue? No one's going to ask me that. We did the ocean, but all right, okay.
Thank you so